Okay. All right, I think they can hear me. We'll see. Maybe the live stream. Okay, that sounds better. Cool. Yeah, so I'm Reese. I'm a fourth-year PhD student at UC Santa Cruz in California. My advisor is Tyler Sorensen, who I know a lot of you know. He's sorry he couldn't make it. Maybe he's watching this right now on YouTube. But yeah, this is a photo I took in Santa Cruz. It's a great place. If you ever come visit, we can take you out surfing or anything else that you like to do. And I think it's also kind of a metaphor for this talk because there's a lot of work in this room on CPU memory models, but I think Simon is the only dedicated GPU engineer who's here right now, and NVIDIA is doing a lot of work on memory models. But there's also a lot of other companies doing work on memory models in GPUs and building frameworks and programming languages for them. So there's a lot of work on memory models in GPUs, and there's not a lot of information on what it actually looks like. And the slides just disappeared, which is a bummer.
It's not so great anymore.
Okay, it's back. All right, maybe this computer just went to sleep. So let's just start out and let's just go through what this looks like. So here's a couple of quotes from a recent paper. I know we have several of the authors on this paper here, and I think, Chung, you're going next. But the quotes are basically, they looked at the out of order, specifically loads to stores, so load buffering behavior, on Power and ARM. And originally they said in the paper that they didn't see any of this on real architectures. And then it turns out you can observe it on Power and you can observe it on ARM architectures, but really you don't see it that often. And so the proposal is to basically remove load to store ordering, which we've seen a lot of today. But the question is, what about on architectures other than ARM or Power? What about on GPU architectures, for example? So if I was on my laptop, I would click on this link and go to it and run an example on my GPU on my system. I'm not going to try that here, but if you have your laptop open, you're welcome to go to this link, gpuharbor.ucsc.edu, and yeah, try it out. You can go, once you're there, go to the Web GPU memory model testing page, and then on the left, there's a load buffer tab, and feel free to interrupt me later on if you do that, and we can talk about what you see if you run it. But the kind of, I guess, the conclusion of that, if I was able to show it, is that load buffering is very visible on pretty much every GPU that you will run on. And it happens quite often, and so it's not going away like it is potentially on CPUs. And so generally, what that looks like, what the kind of conclusion of that is that there's been a large explosion of architectures. We don't just have CPUs. Nowadays, we have tons of GPUs. There's FPGAs, tensor processing units, that's what this is, and FPGAs. And they all implement weak memory models potentially, and they're all super parallel, and so there's new programming models for them. Now, I mostly focus on GPUs because they have the most mature programming frameworks and the most research going on in this area, but I think a lot of the techniques and things that this talk brings up are going to apply to those other architectures as well. And when we think of GPUs, we mostly think of NVIDIA. I mean, they're doing a lot of work in this area, but there's a ton of other companies out there who are doing GPUs. So AMD, Qualcomm, Intel, ARM, Imagination, Apple all make their own GPU. And they all have their own architectures, and they're all thinking about this in different ways. So based on that, this talk goes into two kind of questions. So challenges and opportunities. What are the issues associated with the weak memory models of evolving architectures, and what techniques can we use to address them? And then what opportunities do the design of evolving architectures open up when defining and implementing their memory models? So we'll start with some of the challenges. One is that the implementations are buggy. The compilers are buggy, the hardware is potentially buggy, and so we need better testing methods, empirical testing methods, to actually find these bugs and help companies develop them. Specifically, when you look at these frameworks like Vulkan and Web GPU, which are designed to be portable. So you're not just writing CUDA code for NVIDIA GPUs, you're writing Vulkan or Web GPU code that's supposed to run on every GPU that is made, pretty much, especially for Vulkan. And so what kind of memory models do those have, and how do those implementations cover the mass number of architectures and vendors out there? The other is that the weak behavior profiles of evolving architectures may not follow the rules of CPU-centric models. So when you're developing formal tools and analysis for GPUs, you can't just fall back to what the CPU world has done. And then finally, what Simon was just talking about at the end of his talk is that the interaction between memory model and other GPU features, like forward progress, is complicated, and I'll go through a little example of that. So my work has specifically so far been on implementations, testing them. So we have a paper in ASPLOS last year where we developed a way to evaluate the effectiveness of memory consistency testing. where we basically take this test, which is the message passing test, with release acquire fences, and the question is here, is there a bug in the compilers or the hardware when you actually run this test? And the problem is that let's say you just run this with 2 threads like you might on a CPU, it's not going to observe, you're not going to observe weak behaviors on the GPU. There's too many threads, like Simon was saying, hundreds of thousands, and so you need to add a lot of stress testing techniques on top of this to actually observe weak behaviors. And so then what we do is we create this strategy where we take the axiomatic candidate execution of this test, we mutate it to create a test where we can actually see weak behaviors. We then find test environments where weak behaviors show up more readily, and then we can go back and run the original test and look for bugs in compilers or hardware. And the impact of this is that we actually discovered bugs. So there was this exact bug where they were mistranslating release acquire fences on AMD GPUs. And we also found coherency issues on Intel GPUs on a MacBook. We also integrated these tests into the web GPU CTS, so they use them when they're testing their framework now. And then we followed this up with another experience study at ISTA, where we found more bugs, all coherency bugs in ARM and NVIDIA compilers, and we observed that Apple coherency issue on other GPUs as well. So the takeaway here is that they're buggy. These are the simple 2-thread, 2-instruction tests. Like Peter Sewell was saying earlier, like maybe we need to look at bigger tests, but honestly, in the GPU world, there's still a lot of work to be done just looking at these very simple programs. Now let's look at some new rules. So here's a quote from Paul McKenney's book, where this is the right to read causality test, which is looking for multi-copy atomicity, where you use dependencies to make sure that you're actually seeing non-multi-copy atomic behaviors. And the quote was that someone ran this test on a power system and only saw it 4 out of a billion runs. So the question is that the same case on GPUs? Are they multi-copy atomic? Do you actually see this behavior? Similarly, the ARM memory model has now moved to sequentially consistent release acquire fences. So if you have the store buffering example with release acquire reads and writes, you're not going to see the weak behavior anymore. Is that the case on GPUs? And yet another one, the 2+2 write with release fences, again from McKenney's book, there's a quote that says that this cycle is prohibited even in weakly ordered systems. And the fact that this can't occur also corresponds to a strong release acquire, which is another memory model that was developed by Ori and others. So what does this actually look like if you run it on GPUs? Here's a few GPUs that I ran for this talk. But you can see that load buffering, that's the first test there, is very apparent. It varies from 0.001% on an Intel GPU to over 1% on an AMD machine. If you look at the right to read causality, so multi-copy atomicity, I saw it on 2 machines. I didn't see it on the others. But for example, NVIDIA technically has a non-multi-copy atomic system. So the question is was this that my tests were not sensitive enough, or is there something else going on here for why we couldn't see this behavior? So there needs to be potentially more work looking into what we can do to actually observe that. Similarly, you can see that store buffer with release acquire, none of the GPUs are translating at least to the same model as ARM. They're all giving these weak behaviors. But I guess happily, it seems like GPUs are potentially implementing the same kind of weak memory systems where you can't see this release fence weak behavior that we've kind of concluded you can't see on CPUs too. So just some new rules here, and so when you think about writing memory models and analyzing memory models for GPUs, you have to take into account that there's all these types of behaviors that the CPU world may not show anymore. So memory models are not all we need. So this is the forward progress guarantees. GPUs are not fair schedulers. Like I know the C++ specification doesn't actually really give you liveness guarantees. It says something like threads should make progress, but GPUs don't even go that far for the most part. They don't make progress. So if you have this little 2-thread test here on the right, where you have 2 threads contending for a memory location using compare exchanges, it is totally possible that thread 0 acquires that memory location by writing 1 to it, and then thread 1 comes on the system, kicks off thread 0, and spins forever, and you'll have a deadlock. There's no guarantee in the GPU world that this is going to happen, except for potentially in NVIDIA GPUs, which does give you these types of guarantees. There's also been work on looking from the formal side on how you actually make weak memory models fair. How do you actually give these liveness properties to weak memory models, even in the CPU world? But to extend that to a GPU world or a GPU model might take some more work and is worth looking into. I think Simon showed a little bit of the GPU architecture, but it's because there are just so many threads and there's so many caches, and just how the scheduling works makes this very complicated. However, there are still opportunities in the GPU world that may not exist in the CPU world. And I think there's a lot of exciting avenues of research here and stuff that's already been done and more work that needs to be done. So this is a picture of the Grace Hopper machine, which we already heard about how we can build compound memory models for. But I think actually testing empirically these systems is going to be really important to see what memory models they do support in reality versus what the simulators and the specs say they should. And yeah, and how do the interconnects play into that, and how does this all work out in a real system? And then another opportunity is that the applications we write for GPUs that require synchronization and forward progress guarantees are probably more limited than you would do on a CPU. You're not going to have a GPU where you say every thread contend for a lock. It's just not going to be feasible, and your performance is going to be awful. This is an example of an algorithm that does work very well on GPUs. It's called single pass prefix scan. This was an NVIDIA paper that adds some optimizations to call it decoupled look back prefix scan. And it relies both on release acquire fences and forward progress guarantees to work correctly. But it's a really cool algorithm, and it gives you speedups over pretty much any CPU implementation. So yeah, look deeper into supporting future heterogeneous processors. There has been work on how to combine memory models of multiple processors, but like I said, we need to test these empirically. And it's not just these emerging architectures like Grace Hopper. You know, in your pocket with an iPhone or an Android device, you already have a unified memory machine. You have a GPU and a CPU that are most likely communicating using a shared memory interface. And so what memory models does that support? Is it worth building specs for that type of memory model? Can we get speedups on current applications that we're not looking at because we're not building these types of memory models? There's also work to combine devices other than GPUs. So like what are the semantics of shared memory in Intel CPU FPGA systems? Is a paper by Dan Yorga, and my advisor was on that as well. So looking at other types of architectures. And so we're looking at this right now. We're trying to build tools to run litmus tests across processors and empirically see what the memory models of these systems look like. Now, synchronization is limited. This is kind of a full overview of the work that I think of applications that I've seen people actually write on GPUs. So prefix scan and work stealing queues people write, all of those require release acquire consistency and forward progress. You can also try and fuse kernels or write persistent kernels, which may require scoped or global barriers across threads. But that's really kind of it. You know, they're not doing the super complex transformations necessarily that CPU compilers are doing. Maybe they will in the future, but right now they're probably not in a lot of cases. And so if we actually look at what GPUs are good for, maybe we should be constraining the use cases of synchronization and forward progress and building memory models that are simpler. Can we build simpler memory models for higher level programming languages? And can that lead to opportunities for simplifying analysis of those memory models? Yeah, so that was my just overview of evolving memory models, definitions of we have had modern research advancements. We have a lot of definitions and formal analysis of weak memory models. A lot of this has been focused on CPUs by a lot of people in this room, but GPUs and other heterogeneous processors are kind of the next frontier, and looking into them more from a formal methods analysis and empirical testing is going to be important. And yeah, go ahead and feel free to go to that website and play around with it. You can actually run some of these litmus tests on your GPU, which is kind of cool. Or if you want to look more at my work or get in contact, that's my website. Thank you.
Okay, thank you. Any questions?
So in your GPU testing process, do you also test the atomicity properties, and have you seen something to break beyond the scope of the threads?
Like atomicity as in like an RMW atomicity?
RMW atomicity.
So we have run those tests. We have basically, we haven't seen failures in atomicity of a single atomic instruction or atomic RMW on a GPU. They seem to be implementing those pretty well in hardware.
Okay, thanks.
Yeah.
Okay, any others?
Do you see the 2+2W example also with relaxed tax with
relaxed,
tax?
yes, it shows up quite
with
frequently.
reordering of writes happens.
Yes, all the 2-thread ones show up. basically.
Okay. Another question is, so I originally, I guess it's completely wrong, but thought that GPUs is for race-free concurrency somehow. So do you have actually algorithms that use all these fancy
So
stuff?
the main one that I like to give as an example is the prefix scan. Like it does require on having one thread in the GPU.
Say it again, what is that?
It's called prefix scan, prefix sum, and it basically requires, with these implementations, one thread to pass a message using the message passing idiom to another thread. And so that's really the main, like that kind of, or a work queue where you want to implement like a available work queue. So just spin on a acquire read or something. So those do exist. Like a 2+2 write example, I don't have a good example. I don't know if that would be an interesting one to try and find.
Okay, I think we've got time for one more question.
So we heard multiple times now that on GPUs doing not doing load buffering is impossible for performance. Do we have any data on how bad it would be?
No, I don't think we do have that data. I think one is, we need to find algorithms that actually exhibit this like in relaxed memory, like atomics, and would they benefit from not having it? And I don't think that question has been answered yet.
Okay, great. Thank you very much. I think we'll move on to the next talk now. Thank you.